Good morning, everybody, and welcome back to the 6th Annual Energy Storage Summit. I hope you enjoyed the first session of the morning around what exactly is needed to incentivise and accelerate long duration. Up next, for our first presentation of the day, we have Maxwell Cameron-Jones, who is a process project engineer in electric thermal energy storage with Siemens Gamesa. So Maxwell will be talking around, well, he'll actually be kind of showing us how you can make money beyond the short duration ancillary service market, which is something we discussed at length last week. And I'm looking forward to hearing what he has to say. So over to you, Maxwell.
So hello, everyone. Thank you for joining me on at this webinar today. So I want to take you through ETES, Siemens Gamesa's energy storage thermal, ETES, Siemens Gamesa's electric thermal energy storage technology. And today, to get you from to that point of how we see our technology being able to make money in long duration opportunities, I'm going to introduce you to the technology, how it works, the working principles, how Siemens Gamesa have developed the technology from a concept through to now being ready for commercial deployment around the world. And then also looking at how we see ETES being applicable in a number of different applications, and emphasizing the fact that ETES as an energy storage technology is very flexible. And then looking at some of the market incentives for storage. So we've seen in this energy transition that's continually ongoing, and as we go towards net carbon zero, over the next 10 years, a significant increase in the amount of renewable penetration. We're also seeing an increased amount of market volatility. And we're also seeing a demand for a CO2 reduction, and that's coming from not just carbon pricing, but also government legislation. And along this transition, we're also seeing this commitment to coal phase out. A number of countries have mandated this, and also already coal power stations are being turned off as they're not economically viable to operate. And then there's this pressure for manufacturing and chemical industries to decarbonize, as they too can contribute to the net carbon zero targets. And all of this also comes with the added that heat is a big part of the decarbonization that maybe isn't always talked about, but in terms of energy storage, as we look at electricity, but ETES is able to provide also the heat element of decarbonization. So, but these trends are causing some energy system challenges that the energy storage solution needs to be able to contribute to solve. So we have grid instabilities. It needs to be able to provide more stability to the grid, increase the renewable utilization as we deploy more of it onto the network in capacity terms, but also increase the flexibility of existing generation, whether that's embedded within industrial facilities or conventional generation assets, but also provide a long-term security of supply for capacity and power generation. So the energy storage solution that we need to needs to be versatile, scalable to meet the demands and the scale of the energy transition and the energy market. It needs to be clean and safe over the lifetime, from not just manufacturing and construction, but also at end of life decommissioning and disposal of the asset. And it'd be ungeographically restricted. So the demand for energy storage is different locations around the world in different parts of the network. And so the storage solution needs to be unrestricted in that sense. And it needs to be low cost. So it needs to be able to be deployed feasibility economically, but also not to put additional pressure onto the energy system regarding the cost of our transition. So how can ETES fit into this, and how does ETES tick a lot of those boxes that I was just talking about? So ETES is on the scale of long duration, and what does that mean for us? Well, we're talking in the hundreds, even into the gigawatt hours of storage capacity for both thermal and electrical storage. And in terms of power, we look at the 10 to over 100 megawatt range for the capacity of being able to take power off the grid and put power on, and also to supply heat. So, but why is the ETES technology ideally suited for this? And so we look at the key benefits ETES has. So we can store temperatures, high temperatures up to 800 degrees. It means we're able to be applicable, not just in many industrial applications, but also high temperature steam water cycles. The large duration element comes into the fact that we can scale to meet this demand. There is also the ability to provide heat and power. We have a long design life, so we don't need to be regenerated. We have minimal degradation over the lifetime of the plant. And as we're looking at equipment that is already matured and has long lifetime expectancies, and there's data to back that up. And then again, we are, as said as a need, we are ungeographically restricted. So we only need to have a grid connection in certain grid connection for charging, and then an industrial user to supply heat, or even just to supply electricity again to the network. So now I'd like to take you on to bring to you ETES, and how does our working principles by bringing to you this simulation and animation of our process. So here we have actually the Hamburg demonstration site that we've built, and it shows the complete system, both charge, store, and discharge. So to charge the system, we use an electric blower and heater, and the electric blower blows the cold air over the heater, where the heater converts the electricity to high temperature heat that is then transferred into the air, that then transfers that heat into our storage material that is charged in the process of heating up that rock material until it is fully stored. So that the storage container is made up of rocks, which are heated up and can be kept for a number of weeks. And then when we want to discharge, we run that cold air over in reverse, heating it up, and then transferring it to our consumer, which may be a heat exchanger or a steam generator. In our demonstration site, we have a water steam cycle, which is traditional mature technology used around the world to generate electricity. And here ETES is providing the steam to generate that electricity. And that electrical generator can then provide grid services and active power to the network. So now going into more detail into the different elements of our system and the different major components. So when we look at the charge, ETES is made up of a low-cost electric heater, which is able to utilize low-cost electricity to convert it into heat. We use ambient air at ambient pressure to drive around the system, the heat, and the advantage being is that it can then take those high temperatures and to drive the efficiency of the process. And the electric heater is flexible and fast to respond to the power demand that we can take off the network. So we'll be able to respond to renewable generation, for example. Then going on to the thermal store. So here it is simply a concrete, insulated concrete container containing volcanic rock. And we chose volcanic rock because it's a low cost, widely sourced material globally. And so we're able to meet that large scale applications. And by having the concrete container insulated with standard building construction materials, we can store the heat up for a number of weeks. And then looking at the discharge process, we can, as I said, transfer that heat into a steam generator, and it can then drive a steam turbine and generate electricity, re-electrifying the heat back to electricity and put onto the grid. Or the steam could be used directly in a steam network for an industrial user, or the heat could be directly used in high heat user applications such as the steel industry. So now I want to take you along the journey of how Siemens Gamesa have developed ETES from a concept through to now being commercially ready, working with our engineering partners around the world on a various number of projects. So the concept of storing heat in rocks was tested at our test facility, and here it really demonstrated the concept of using hot rocks as a thermal storage media. And we are able to then test a number of different configurations of the storage and also the operation and also the storage material. Then into the demonstrator, we have demonstrated the full cycle. So we are demonstrating the charge, store, and discharge of the system, and also have by being connected to the network, the local distribution network, we have been able to demonstrate the capability of being able to provide some grid services and value to the network. And now that we've gone from successfully demonstrating the full cycle of the ETES system, we are now working with engineering partners around the world, and with these engineering partners and their supply chains and the supply chains that we have developed as well, we are able to then deliver the projects at scale into those tens to hundreds of megawatts of power and many hours of duration and capacity, as well as providing those high steam parameters for industrial users and steam turbines. So, so now I want to take you through how we can see ETES being applied. And here, ETES, there is a number of different applications, and this is where I also bring the title of the webinar into, in that how do we then generate revenue from these opportunities of decarbonization and increased renewable utilization. So firstly, ETES switch. And here what we're using is conventional power station assets and extending their life, giving them a second life. So you've got a water steam cycle, and either for example, in a coal power station that is either mandated to shut down or is uneconomical to run and be fueled on coal, ETES can replace that carbon emitting boiler that's being fueled with fossil fuels to then decarbonize that and but also give a long extend the economic viability of that asset by increasing its flexibility, but also generating revenue from renewable electricity. But also, most importantly, we're utilizing an existing capital asset that's already connected to the network at large scale, and is how we see it as being able to deploy large amounts of storage to the network. If then look at the ETES add application, and here we're aiming to decarbonize industry. So I mentioned at the beginning that heat is an element of the energy transition that is very large in terms of the thermal power and the quantity of energy we need to decarbonize. And here ETES can be used to replace, say, a fossil fuel powered boiler to generate heat, and ETES can then be integrated into the existing industrial users' heat demand, but add flexibility to the power station, flexibility to the industrial plant by utilizing the changes in prices of electricity, but also providing some level of grid security and supply by generating revenue from things like constraint management. And this is where something we've seen in the UK with the pathfinders is an opportunity that ETES add could be used in, where we're generating revenue from the charging side of the energy storage system. And then through to ETES base. So where we identify an application where there is a requirement to be connected directly to the transmission network, but not just in the charging part of the process, but also discharge. So we're looking to re-electrify the heat, and we're looking to provide those services or stability of supply, security and stability of supply through generating electrical energy. And here, this is what we've got in Hamburg, as I showed you with the animation, the complete system. So you've got the charging, storage, and discharge with a water steam cycle. And the advantage here of ETES Base is that you're then able to install it wherever is needed on the network, or co-located with, say, a solar farm, a solar park, or a wind farm. And the ETES base can be a part of that renewable installation, and then provide additional revenue streams, for example, grid services or increasing the stability of the network. So by looking at these three applications, it can be seen that there are a number of different revenue opportunities along the electricity value chain. So not just from the electrical generation, where we're offering the value of increasing power station flexibility, but also providing electrical generation in ETES base, and thus utilizing the opportunity of those capacity payments, or just even on the open spot price market, utilizing arbitrage between high and lows electricity prices. But then looking at the transmission, we're able to provide security of supply and increase grid stability. So we're already seeing in the UK a number of grid stability services that have contractual value. And then looking at behind the meter, where we're looking at those industrial users, there may be added benefits to reducing, say, the input power from the network, or providing increased flexibility that the local network demands and values, for example, in grid constraint management, or taking surplus power off the network to prevent, and thus preventing wind curtailment. So how do we incentivize commercial solutions in terms of energy storage? So we're looking at the current market, right? And so we're seeing that the market is becoming increasingly volatile, with highs and low pricing differences. Wind is being significantly curtailed in many networks around the world. And there are a number of different other project revenue streams that we can see that other generation assets are looking at, are already generating revenue, such as stability or capacity. And this creates a really good opportunity for energy storage to tap into those technical and market challenges. But to transition and to be able to really build the commercial business cases for energy storage, there needs to also be regulatory framework support. So, for example, wind generation at the moment gets priority dispatch onto many networks. And so the incentive for wind developers isn't always there to build energy storage. So the regulators need to look at how can, along with deploying more increased renewables, include an element of energy storage. And that comes from how energy storage is recognized in terms of taxation, but also regulations in terms of the definition of energy storage, whether it's a generator or a consumer. And by working with policymakers, we have started to have conversations about what ETES and long duration energy storage needs to be able to build those strong business cases that really drive the business models for long-term financial capital support for projects. And we are already seeing these opportunities and revenue streams in a number of key markets. For us, we've seen that for example, in the Netherlands, there's the CO2 reduction incentives, and long duration using renewable energy to charge can take advantage of those. And then in the UK, we've had the National Grid Pathfinders. So both the Stability Pathfinder offers us a revenue stream from the fact that we are a rotating generation asset with our steam turbine. But then also this Constraint Management Pathfinder, where it's looking to deal with alleviating grid constraints. We see an opportunity there for ETES as well. So to summarize, I want to take you through from the start. So ETES is a mature uses many mature components and equipment that is already well understood in their operating lifespan, and the supply chain is there in the scale that we need to deploy the technology to deal with these energy transition challenges. ETES as a design and system can be flexible to meet both those electricity supply demands, but also heat, as I explained, with the different applications. And it also can be customized in scale to meet the business case needs of every single project. And then, as I said, ETES is scalable, and by the fact that we are utilizing a low-cost storage material, along with traditional construction techniques in terms of its using construction materials, but also the construction methods of building the plant is similar to those of a power station. that have been built many times before around the world, we can then get to that large scale that we need. But also ETES, in terms of as a technology, doesn't impact negatively on the environment with the materials that it uses, or with the requirements for in construction or operation, but then also disposal in comparison to, say, other energy storage technologies. So thank you very much for listening, and looking forward to taking questions.
Great, thank you so much, Maxwell. I think that was a really interesting and insightful presentation, particularly highlighting the kind of available revenue streams with this technology, and obviously the fact that there's no negative impact on the environment is pretty key, I think, for any kind of viable future technology, particularly for energy storage. So we do have a couple of questions, which I'll jump straight to so that we don't. So make sure we get them covered. So we're talking, when we're talking about round trip efficiency for ETES.
Yep.
How does that change with different levels of charging and discharging power? Is the first question on that.
Yep. So when you look at ETES from a heat to heat application, so that's taking electricity from the network, converting it to heat, storing it, and putting the heat back. ETES is very efficient in the 90% range, because you're just converting heat to heat. And then the discharge part of the system, if you're obviously discharging to heat applications, then it's we're in those high 90s. In terms of then re-electrification, we're using the water steam cycle, so we're then utilizing between the 30 to 45% efficiency of a water steam cycle. And obviously at those larger scales, to particularly answer the question, the efficiency increases with larger powers. But we do see that there isn't, say, a drop off there's actually a gain in as you get larger in the system. So larger, long durations and higher powers, we get to higher efficiencies, and more the better the case is for ETES as a project.
Great, thank you. And just adding to that, can you comment on the RT changes for weekly or daily cycling? And can you give an indication of thermal losses that would happen over time?
So in terms of operating, how regularly you want to operate, so we see when we're looking at business cases, the more frequently you discharge and charge, the higher the revenue opportunity, because you don't tend, at the moment, the market isn't, say, paying for storage part, but it's paying for either taking power off the grid or putting power onto the grid. In terms of how that affects the efficiency, there isn't a significant effect at all in the number of times we charge, or the power that we charge at in terms of being at the rated power. And then in terms of the storage losses of the energy capacity, we only see a minimal loss in the less than sort of 1% per day. So, and even then, even after a number of 2 or 3 weeks, we don't see a significant performance loss of the power that we're discharging either.
Great, thank you. I hope that's answered all everybody's questions on RTE. Can you give any clarity on how many minutes it takes from charging mode to discharging mode?
Obviously, it depends on how the system is configured, and we can, in terms of the materials we use, but we're talking in terms of minutes, in terms of being able to switch between charge and discharge, because obviously once the system is hot, then it's faster to charge, faster to switch between the two.
Great, and I'm sure any other very specific questions around kind of timings and amount of time from charge to discharge, Maxwell and his team will be happy to take any kind of further questions via email or through the portal, of course. And one final question from the audience. So what experiences do you have with electric heaters and ETES, and what's the max temperature that you can achieve?
So in terms of Siemens Gamesa's experience, we have the demonstration site which has a 5 megawatt electric heater, and we're working with supply chain to build those electric heaters up to the much higher tens or even hundreds of megawatts of power to charge for our larger applications. In terms of the temperatures, we are expecting to see and with the supply chain up to 800 degrees from those.
Nice, thank you very much, Maxwell. Just going back to something you mentioned in terms of being geographically unrestricted, obviously that's a great benefit for your technology. Aside from where your kind of commercial pilot is happening right now, where do you have any other examples of where your technology could be efficiently utilized or could be very, very well suited to that you'll look to roll it out in the future?
Yeah, so an area that I think particularly ETES is advantageous is the ETES add application that I explained. So where there is large industrial heat demand, where you're trying to electrify a large heat demand, and here ETES can be used to store that intermittent electricity from renewable sources and utilize the low prices of renewables low prices of electricity during certain times of the day or even week, to then discharge that heat into the heat network of an industrial user. And because we're a low cost storage material, we can store thermal energy and large quantities of it at very low prices in terms of capex.
Great, thank you. Just going back, I hope you don't mind, going back to answering the question around the RTE. Yeah. What would be the overall RTE from?
So as I said, sort of the heat, when you look at the process from heat to heat, then you've got that high 95, and then transferring that into re-electrification, so the AC to AC, then we're looking at between 30 and 45% RTE, but it really does depend on the water steam cycle technology that you're using, and higher temperatures and pressures obviously drive the efficiency of that up. But then in terms of the ETES part of the system, we're very efficient in delivering that heat to the steam water cycle.
Great, lovely. Yeah, so as I said, any further questions, feel free to direct them to Maxwell and the team. And we are coming up against time. So I just want to say, I mean, for me personally, obviously, I think it's really exciting that you're kind of, I've seen this go from concept. So last February, we had Siemens Gamesa on a panel at the last live event that we were able to run. And obviously now you've taken it from kind of concept to an actual commercial pilot. So I think that's really exciting. Yep. And it seems there's a lot of exciting things ahead for ETES. So thank you so much for getting involved and for sharing your insight on your presentation. And I hope you enjoy the rest of the sessions. And as I said, feel free to get in touch with Maxwell and the team. Thank you, everybody, for listening.
Thank you.
Thank you. Bye-bye.
Bye-bye.